Alright, so welcome to Organic Chemistry. We're going to start with Chapter 11, which is the Introduction to Organic Molecules and Functional Groups. So what we see here is a patient in a dentist chair. Lidocaine is a local anesthetic, which is an organic compound. So when we're looking at organic chemistry, we want to first define what organic chemistry is. And organic chemistry, for our purposes, will be the study of carbon-containing compounds. Okay, so when we're looking at organic chemistry, this is going to be dealing with structure. We'll be looking at properties of different organic compounds and different reactivity of various carbon-containing molecules. So the pictures that we see here include oral contraceptives, plastic syringes, antibiotics, and synthetic heart valves. And all of these things are made up of organic molecules. We might see them also in clothing, food, other medications, gasoline, refrigerants, and soaps. These are all made solely of organic compounds. Some compounds like cotton, wool, or silk are naturally occurring, or they can be isolated directly from natural sources. And we also have others that are synthetic, such as nylon and different polyesters. Organic compounds have different characteristic features. All of these compounds that we see have carbons in them, as we've already defined organic chemistry as any molecule that contains carbon. In its simplest form, we have a carbon with 4 hydrogens, which is methane. You can see the picture of methane there. Ethanol is an organic compound. Capsaicin is the active component in peppers, which can also be used in arthritis pain relief. And caffeine is an organic molecule that we probably consume daily. All organic compounds contain carbon and hydrogen atoms. Carbon always forms 4 covalent bonds. In the periodic table, it is in group 4A, which means it has 4 valence electrons. So if we're drawing the valence electron structure for carbon, that's what we would see. And hydrogen, which is not on this mini periodic table here, has 1 valence electron. And that forms 1 covalent bond. So if we had 4 hydrogens, and they're all going to contribute 1 electron, which is what is shown here, carbon can form a single bond 4 times to hydrogen. And each of these lines represents the 2 electrons. And this again is the structure of methane gas. That line illustrates 1 bond which contains 2 electrons. Carbon can also form a double bond in addition to the single bond that we just drew. So this would be our double bond. This is the single bond. And we can also form a triple bond. So if we were to draw this out without the dots, this is carbon with a single bond. This molecule happens to be ethane. Carbon with a double bond. This is ethylene. And then carbon with the triple bond is acetylene. All right, and we're going to notice if you count up all the bonds that carbon is making, each carbon has 4 bonds. It may have 2 bonds to the same carbon, but in total they all have 4 bonds. We can also see below here the structure of propane, where each of these carbons has 4 bonds. This is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So that's propane has 3 carbons. We can also have the cyclic structures, such as cyclopropane. These both have 3 carbons, but this one has less hydrogen. But this carbon here is still making 4 bonds. Organic compounds can also have other elements besides carbon and hydrogen. Any atom that is not a carbon or hydrogen is called a heteroatom. So we've seen hydrogen and carbon. The other heteroatoms that we're going to see a lot of include nitrogen, which has 1 electron pair, an oxygen, which has 2 electron lone pairs, and then the halogen. So these we'll see come up often. So hydrogen normally likes to make 1 bond. It has 0 unpaired electrons. Carbon, we've already known it has 4 bonds. That one has 0 unpaired electrons. Nitrogen makes 3 bonds. It has 1 pair of lone pair electrons. Oxygen makes 2 bonds. It has 2 lone pairs. Halogens make 1 bond, and they have 3 pairs of unpaired electrons. If you forget, you can go back to look at where nitrogen is on the periodic table. This is a group 5A element, which means it has 5 valence electrons. So if you're drawing nitrogen and it has 5 electrons, count 1, 2, 3, 4, 5. So the paired ones are going to end up being our paired electrons that are extra, and the single electrons is where we can form bonds. Okay, so if we see an example here, this is the structure of methanol. That carbon is making 4 bonds. Oxygen has 2 lone pairs. So again, carbon has 4 bonds. Oxygen has 2 bonds and 2 lone pairs. And in the situation of formaldehyde, carbon still has 4 bonds. Oxygen has 2 bonds and 2 lone pairs. And for the carbon, 2 of its bonds are going to the same atom, resulting in the double bond. This is the structure of formaldehyde. Carbons generally form 4 bonds. That means it's tetravalent. Something that is trivalent forms 3 bonds. If it's divalent, it forms 2 bonds, and the halogens are monovalent, as is hydrogen, that forms 1 bond. So anytime we encounter these practice problem slides with the little skills checkbox in the upper left there, you should feel free to pause the video and run through the problem and then unpause the video to see how you did. Which chemical formulas represent organic compounds and which represent inorganic compounds? So if we think about our definition of what an organic compound is, this is one that contains carbon. If I look at A, that one is C6H12. This one is organic. Water is not containing organic, so this one would be inorganic. Magnesium sulfate is inorganic. CH4O contains a C, so this is organic. And sodium hydroxide is inorganic. Here's another problem. So you can pause the video if you like and attempt to draw in all your hydrogens and lone pairs for each compound. And then you can unpause the video or just play through. So we want to remember carbon makes 4 bonds. Hydrogen makes 1. Our halogens, which are chlorine, fluorine, iodine, bromine, those make 1. And they have 3 lone pairs. Just going to abbreviate electron there with the E minus. And oxygen makes 2 bonds with 2 electron pairs. Nitrogen is 3 with 1 electron pair. So for A, I need this carbon to have 4 bonds total. It's currently making 1, so I need to draw in 3 hydrogens. This one needs 2. And the chlorine has 1 bond already, but I need to fill in the electron lone pairs. So there should be 3 total here. For this carbon, I have 1 bond, so I'm going to add 3 more to hydrogen. This carbon is making 3 bonds already, so there's 1, 2, and then double bond, 3. So I need 1 hydrogen here, and oxygen gets 2 lone pairs. The carbon in C, this one needs 3. The carbon connected to the nitrogen already has 4 bonds, so 3 to the nitrogen and 1 to the other carbon. So that doesn't need any hydrogens, but this nitrogen needs a lone pair. For organic molecules, the most stable arrangement of atoms keeps the groups as far away from each other as possible. So in the ball structure there that we see of methane, there's the carbon that's in black and the 4 hydrogens. And you can see it's kind of in a pyramidal shape, or in a pyramid, where all of the hydrogens are as far away from each other as possible. So one of the ways that we have of drawing these tetrahedral carbons, we're going to draw 2 atoms in the plane. So the straight lines indicate that it's in the plane. So if you can think of your piece of paper as the flat, these are lying flat on your piece of paper. When we draw something dashed like this, hydrogen, the dash indicates that the bond is behind or away. So if we use that piece of paper, your hydrogen is sticking out of the bottom of the piece of paper. And then we have another hydrogen here that is in front of the paper or coming out. Okay, so all carbons that have 4 single bonds are tetrahedral. And so any that we see here, your carbon that's tetrahedral will have 2 bonds in the plane, 1 wedge, and 1 dash. All right, and we'll notice there in the bond angles of these tetrahedral carbons that they're 109.5 between the 2 hydrogens there. If you have a triple bond, your acetylene that we drew earlier, which we can also draw this way, the hydrogens are coming straight out of that carbon, so this bond angle is 180 degrees. It's linear. And then for the ethylene, the bonds here are 120. Structures with different numbers of atoms and lone pairs can adopt different geometry. So if we have 2 groups in a structure that involves 2 atoms and 0 lone pairs, this is a linear structure. And the bond angles are 180. If you have 3 groups, 3 atoms, 0 lone pairs, this is trigonal planar. And this is 120 degrees. For 4 groups, 4 atoms, and 0 lone pairs like carbon, this is tetrahedral. And our bond angle is 109.5. For 4 groups, so that group can include the electron lone pair cloud. So we have 3 atoms and 1 lone pair. This is trigonal pyramidal. These are around 109.5 as well. For 4 groups, 2 of them are atoms, 2 are lone pairs like water. This is bent. And that is also around 109.5. If we look at this problem, we are asked to draw the structure of each of these compounds using the solid lines, wedges, and dashes to show 3D shape around each carbon. So one thing you want to remember is we need 2 atoms in the plane, 1 wedge, 1 dash. So for our first one, you can pick any to be in the plane. So if I'm gonna use the C and the Cl and the top H will be in the plane. Then we just need 1 wedge and 1 dash. And you could have used the other atoms to be in the plane. So I could use this hydrogen here, these 2 in the plane. I could have made this one wedged and this one dashed. For the second one, if I use the second carbon bond and this hydrogen in the plane, this hydrogen can be wedged, this one dashed, and I might want to use this Br as my in the plane, this hydrogen to be wedged, this one to be dashed. Both carbons each have 2 atoms that are in the plane and 1 that is wedged and 1 is dashed. We're being asked to determine the shape of each carbon in dimethyl ether. If we look at carbon, it has 4 groups, no electron lone pairs. This carbon is tetrahedral. As is the other one. So this is referring to the table 11.3 that we saw a couple of slides ago. We can scroll back. It had 4 groups and 0 lone pairs. The other structure was oxygen with 2 atoms, and oxygen we know is going to make 2 lone pairs, so I'm going to draw those in. So if we have 4 groups total, 2 atoms it's bonded to and 2 lone pairs, that's bent. So this oxygen is bent. And our lone pair oxygen, we've drawn the lone pairs in on already. Okay, here's another practice problem. Determine the shape around the indicated atoms in each compound. So we're looking at 1. The number 1 there on that carbon, it has 3 groups and no lone pairs. So that one's going to be trigonal planar. And again, this one's using table 11.3. Okay, this second carbon also has 3 atoms and no lone pairs. These are both trigonal planar. Okay, for 1, we have 2 atoms bonded, 0 lone pairs. This one is linear. Carbon with 4 atoms, or 4 groups, and no lone pairs. This is tetrahedral. Oxygen has 2 atoms, 2 lone pairs. This is bent. As we take organic chemistry, we're going to be drawing a lot of structures, and to draw out every single carbon and hydrogen bond is going to be a very tedious task, and we certainly don't want to draw them out in ball and stick model. So there's 2 different ways that we can shorten this. In the first structure in A that we see there, we're showing all of the atoms and all of the bonds. And the ball and stick model shows the same thing. It gives it a little bit more 3D structure to it. So this has a 3D structure to that. When we're drawing the condensed structure, we remove the bonds and group the hydrogens together. I'm going to number these carbons so I can keep track of them. The number 1 carbon has 3 hydrogens, so I'm going to write CH3. Number 2 has 2, so this is CH2. Number 3 is CH2. 4 is CH2. And then 5 is CH3. Okay, so that is one way to do a condensed structure. And there's one more way that we can shorten it. So I can write my CH3. And all of these CH2s are the same, so I can cluster them together in parentheses. So that's CH2, and I have 3 of those, so I can just list it that way, and then CH3. The really short way to draw these is the skeletal structure, or the zigzag. And that shows the carbons as points, and we don't even draw in the hydrogens, those are implied. So for pentane, which has 5 carbons, I'm going to put my pen tip down and then count to 5. So 1, 2, 3, 4, 5. Each of those points represents a carbon. And the H's are implied. On the condensed structures, all atoms are drawn in. Electron bond lines are eliminated. You can also omit the lone pairs. For this first one, the CH3 in blue can be written out as CH3. The CH2s can be written out as CH2. We have another CH2, which is in the orange box. I'll just do this. And then we have another CH3 on the end. So on that top example there, we can shorten it like we did on the last slide, where these two CH2 groups are bonded together and they're the same. We can shorten that using the parentheses. So CH2, we have 2 of those, and CH3. So with this next example, we have a CH3. In green, we have a CH, and the book likes to stick a vertical line up for this other CH3, so you can see that it's coming off of there. We have another CH2, and then the CH3 at the end. And one way to shorthand when you have the 2 groups on the same carbon, you can see there's 2 CH3s attached to that green carbon. I can draw out the green carbon as CH, and attached to that is 2 CH3s. So those are 2 of them bonded to that same green CH, and I have CH2 followed by the CH3. Okay, so here's a couple more problems that we can work on. So we can shorthand this. I have a CH3 and a CH2. The H's usually go with the C, so I'm going to do CH. And you can draw a vertical line down for that CH3. We have another CH2 and a CH3. Alternatively, we can put whatever is in the blue box in parentheses if it's coming off of that. So the same thing here would be CH3, CH2, C with that orange H, and then in parentheses I'm going to do CH3. So that one's coming off of the carbon preceding that, and then we just have CH2, CH3. For a double bond, we can actually draw the double bond in there. So we have a CH3, CH, and then you can draw the double bond here, CH and CH3. I've also seen it where the double bond is left out completely and you have to figure out that it's a double bond, but it is nice to draw it in there so that you can look and see that immediately it's a double bond. Okay, so with heteroatoms, it's no different. What I'm going to point out here is there's 2 CH3 groups on this same carbon. So I'm going to do CH. I'll just put an asterisk there so you know it's that one. And there's the 2 CH3 groups on that CH. I have a CH2 and then an OH. And you can draw the lone pairs in if you want to, but you don't have to. Here I have a CH. There's 2 chlorines on the same one, so I'm just going to put Cl2. There's 2 CH2s. There's an O, and then a C, and there's 3 CH3 groups on there. So that carbon didn't have any hydrogens, so that's just C with 3 CH3 groups. So on this slide, you can take a chance and convert a couple of these to condensed formula to get some practice. I'm just going to go ahead here. These are the same groups. They're all CH2s. There's 3 of them. Then the CH3. Here we have a Br, CH2, CH2, Br. You could also write it that way. And then for the last one, this is a CH3, this is a CH3, this is a CH3. They're all connected to that same one. So I'm going to do C, CH3. There's 3 of those. So I'm working backwards. I have a CH2 and then another CH3. All right, and then here is where we're going to do the opposite. We're going to convert them into a complete structure with all lone pairs and all heteroatoms. So we're going to show all of the bonds. So here is a C with 3 CH3s. Then I have a C that is a CH2, an N with 2 hydrogens, and that nitrogen needs a lone pair there. And for the next one, I have a CH3, a CH2, oxygen, which gets 2 lone pairs, a CH, and then 2 CH3s. Okay, and this last one, I have a C with 3 H's, a C, okay, a C with 3 H's, a C to 3 Cl's.